Hello and welcome to another tutorial. In this tutorial I am going to conclude our discussion on polynomials. In the past tutorials we discussed about the basic properties of polynomials, especially how to implement the evaluation of a polynomial at a given point in a most efficient way, which is the Horner's method. And if the degree of polynomial is n, Horner's method only takes 2 times n operation and precisely n multiplications and n summations to get the value of the polynomial. And then we also implemented the addition and subtraction, and the result of addition and subtraction is always a polynomial, and the coefficients basically add term by term. And we discussed that for the multiplication the result is also always a polynomial, and the multiplication, the coefficient, is the convolution sum of the coefficients of p and q. Now the catch here is that you have to make sure the p and q may not have the same degree, and therefore if you implement this in exactly this way in Java, we will run into array index out of bound exception for one of these two polynomials, okay? Because the coefficient array in each polynomial is the size is degree plus 1. But there is a way that we can avoid that error, and I'll show you how to do it. So for the division, we said that the problem with division is that the result is not always a polynomial. So we cannot divide two polynomials and return a polynomial. What we can do, either create another class called a rational class, rational object, and rational object is basically a fraction with a polynomial as its numerator and another polynomial as the denominator. So when we divide two polynomials, either we have to return a rational object, or we can return an array of two polynomials, one for the quotient, the result, and then one for the remainder, okay? So when we divide two polynomials, we also end up with the remainder, and the degree of the remainder has to be strictly smaller than the degree of the q. So let's head to Eclipse, implement the multiplication, and come back and conclude this topic. So in the Eclipse, what I'm going to do, just like when we did with the functions, I'm going to create a static field, public static polynomial x. This is the base polynomial, new polynomial 0 and 1 basically, okay? This is the polynomial x, and if you recall, we already implemented the overloading for addition and subtraction. And for negation, what I did was I created a private method called times, and the input is a double value. And basically with this we take a double value multiplied by the polynomial. So each coefficient of the result is basically the coefficient of the original polynomial times the double value v, okay? Now when we negate a polynomial, we just multiply it by -1, all right? So far this is just multiplication by a real number, a double number. So in order to make use of this x base polynomial, we have to use import static from the polynomial class everything. So this imports static fields and methods in polynomial, okay? And let's test it. So polynomial p6 equals for example x plus 3, and system.out.println p6. so this should return x plus 3. And again, just like we did with the functions, so operator overloading allows us to construct a polynomial object in an intuitive way. Okay, and this is very nice and beautiful. Okay, I like to call it the beauty of operator overloading. And since we have also implemented negation, I can write minus x plus 3, and the representation is minus x plus 3. Okay, and finally multiplication. So I have already written it, and I'll just go through the explanation. Times, so there's a, let's make it private because we're going to use it for operator overloading. Private polynomial is the return type, times, and this basically takes a polynomial as an argument. So what I do first is make a copy of this original polynomial. Remember, we don't want to mutate our polynomial. We just want to return a new polynomial. So I like to make a copy first. And then the degree of result of multiplication is the sum of the degree of P and Q. All right, that's the first rule. And then I create, and now because I know the degree of the result, I can create an array for the coefficients of the polynomial of the result, which is the size is degree plus 1. Okay, and then we have this convolution sum, multiply coefficient at some index m, and m runs from 0 to degree mult, is p at the coefficient of p at index I, the coefficient of q at index m minus I, and this sum runs on I, runs over I from 0 to m. Okay, so this basically shows that we have to have two for loops inside each other, one for going through the indexes of the mult, and the other for loop for calculating this summation. Okay, so because the degree of P and Q may not be the same, if we write the sum like this and go from 0 to m, when m goes beyond the smaller degree, we run into an array index out of bound exception for one of the two. So what I do, the easiest thing to do is to create a copy array of the coefficients of P, and an array which I call it the extended array, the extended coefficients of P and extended coefficients of Q. And both of these two extended arrays have the same size as the size of the coefficients of the results. Okay, and then from the index 0 to degree P, I copy the coefficients of P into extended array for P. Similarly for Q, from 0 to degree Q, I copy the coefficients of Q in the extended coefficient array for Q. So basically these extended arrays for coefficients are the same from 0 to the degree index, and then the rest are 0. And we don't care about the rest, right? We only do this because then when we run this sum, we don't run into any exception for the size of the arrays, because now they both have the same size, and they have also the same size as the size of the result. Okay, so we write a for loop going through the calculating the coefficients at each index, and then another for loop for calculating the sum. In order to calculate the sum, I use the plus equals operator. Okay, so it calculates, and remember this is a new array, so each element is 0 by default. And then each time this operator basically calculates the pi times qm minus I, and then adds it to the previous value. And then finally we calculate all the coefficients of the result, and then we return a polynomial with the new coefficients. And then in order to be able to do multiplication, I just implement the operator overloading. So we have to have multiply, and then double V, and then return this dot times V. Okay, and then we have to have similarly multiply reverse, doesn't matter, and then we also have multiply with parameters, with polynomials. as parameter instead of a double value. And again, we have these times for polynomials too through method overloading, which takes either double or polynomial, so it's just the same syntax. Okay, now the beauty is very easily seen. So using this base x, now I can write, for example, 2x. I can multiply a double value by x and it still works, because now it takes advantage of the operator overloading for multiplication of a polynomial with a double, and also overloading the operation of addition between a polynomial and a double. Okay, and then if I want to create higher order polynomials, I can just say x times x times x minus 1, sys out p7, x cubed 0x squared 0x minus 1. Now I think it's a good idea to go to the toString method and try to eliminate the coefficients that are basically 0. So here when we go through the coefficients, this coef value, and what I'm going to do here is that if so we get this coef value, the magnitude, and then I'm going to say if coef or math.abs coef is less than 1e negative 8, for example, just continue. Okay, coef is a string actually, so we just take this and we put it here. So what I think is going to happen is that if it's 0, so our tolerance for being 0 is 1e8, 1e negative 8. You can set anything you want based on the order of the coefficients that you're working with. Continue. Here the continue means okay, let's try this. Right, okay, so now we get, so what happens here, basically if you are not familiar with continue says skip. When you put continue in a while loop or a for loop, something that is a loop, skip the rest and go to the next iteration, okay, to the next step. So basically what I'm saying here is that if it's close to 0, just don't skip the rest, just go to the next step, and that avoids 0 coefficients. Okay, so this is another trick for making the toString representation nice. Now note that I didn't use equal, for example 0 double or 0d or 0, because equal is not recommended for double values, because these don't have exact precision. These are, if you can use this for integers or bytes or shorts or longs, but for doubles and floats it's not recommended to use equal. Instead we use the equality based on the difference or the distance of the two numbers and some tolerance. Alright, so this is x3 minus 1, and then we have minus 2x plus 3, and then polynomial p8 is p7 times p6, and then let's print it. minus 2x4, 3x3, 2x minus 3. And again, you see that the x to the second power is not appearing here because the coefficient is probably turning out to be 0. And then the toString method just skips that 0 coefficient. Okay? So x to the fourth is just minus 2 times x cubed, so minus 2x4. And then we have 3x3, and then we have minus 2, we have 2x minus 3. So p minus 2x plus 3. Okay, and then x cubed plus 1. This is correct. We should have 3x cubed minus 2x plus 3. And the reason here is that okay, no, so x cubed minus 1, this is x cubed plus 1. Why is that? X cubed, so if we delete this, we end up with x cubed and plus 1, x cubed plus 1 minus 1, x cubed plus 1. So apparently the operator overloading is not working for subtract. Let's try just x. X minus 1. X times x. X squared plus 1. Why does it become plus? Let's see if we define it with the new keyword, new polynomial. 0, basically minus 1 and 1. So we have x minus 1, okay, and then 0 here, 0 here, and then 1 here. This is x cubed negative 1. It becomes plus 1. Oh, that's okay. Yeah, so the problem here is that okay, I see. Okay, yeah, we should take more care here because the coefficient of the next term is defined, the plus or minus is defined by the previous term, and if we skip it, we have to make sure that we're skipping the yeah, so let's comment this out. X cubed plus x squared 0 minus 1. Yes, so let's skip that out, and you can later on as a homework try to fix it. So x minus 1, x cubed minus 1, and we have minus 2x plus 3, and when we multiply we get minus 2x cubed, 3x3, 0x2, and then we still get we get minus 2x times minus 1, we get plus 2x plus 3 minus 1, we get minus 3. So the multiplication is correct, and the operator overloading is also works. And obviously we can do something like 2p8 minus 3, for example. And finally we can go here and define the division by a real number, public polynomial, or basically we can copy and paste what we had here, divides with double, and this one we just divide it. Alright, and then here we can have public polynomial divide or divides, I'm not sure, divide, okay, divide double V, and this going to, okay, we add the S here, so divide is return this dot divides V. But we cannot do the reverse division because reverse division is a number divided by polynomial and it's not a polynomial. So here I can also have 2p8 over 3, for example, and it still doesn't complain because the division by a real number has been implemented. All right. Okay, so I think this is basically it in terms of the polynomials. Oh, okay, one last thing that we have to implement is the composition of polynomials. Composition, basically PQ of X. And in order to do that, I'm going to, now that we have the operator overloading, I am going to use the code that we wrote for the okay, I think we already had this here. Let's delete this. For the Horner's method, and we're going to again use the Horner's method to evaluate the polynomial. How do we do that? So we call this compose, and we pass in a polynomial, for example Q, and then what we are going to do here is instead of having the value X here, we put Q. Now obviously the problem here is that the problem is that this value is not a polynomial. So basically instead of having a double for the value, we have to have a polynomial. All right, and then it should start with the basically we can write 0 times x plus this. So this is 0 polynomial plus this number. Okay, so it starts from this number, we add the polynomial Q, and then we return value, and obviously the return type is also polynomial. So again here the value is a number as polynomial. I could just also type a new, so another way to write this is just new polynomial this. Okay, but I guess because we already have the operator overloading for multiplication of addition, that looks nicer in general. Now let's go and test this. So polynomial P9, let's call this x2 plus 1, or maybe just x2, and polynomial P10 is P9 times compose x plus 1. So what I should get is x plus 1 squared when I print P10. X cubed, x is, so we have 0 for x cubed, 1 for x squared, 2 for x, and plus 1. Okay, and the reason that we have this x cubed term with the coefficient 0, because when we write it this way, 0 times x plus coefs, it is going to assume that the degree of this polynomial is 1, which is actually 0, right? So if I write it in the way of polynomial value, new polynomial, this coef degree, then now value has a degree of 0. So this should start from x squared, right? X squared plus 2x plus 1. Okay, so this is it. So one last thing that remains is finding the roots. Now, in order to find the roots, instead of directly implementing it, because it's a little bit complicated, what I'm going to do, I'm going to take another approach. Now, there are other useful libraries that implement polynomials, and one of them, very useful one, and I highly recommend, is from Michael Flanagan. It's called Michael Flanagan's Java Scientific Library, and Michael is a professor at the University College London. So the archive file, basically a JAR or jar file, Java archive file, is available on Michael's personal website, www.ee.ucl, University College London.ac.uk/m Flanagan/Java. And there is a source code also available on GitHub. I think it's not the complete Java archive, it's just most of the libraries, not all of the classes. And actually I'm not sure if it's a Maven build or not, but anyways, you can find the source code for most of the classes on this GitHub address, github.com/bgithub1/Flanagan. And for example, this Flanagan, the polynomial in the Flanagan library has methods for calculating the roots of a polynomial. So instead of writing the root, finding the roots from the scratch, you can just write an adapter method. And what this adapter method does, it converts your polynomial class to a polynomial of type which is from the Flanagan library. And then when you convert it, you call the finding roots method on that polynomial. So this is how you interface your class with the other classes in other libraries, because even if the two classes have the same name as polynomial, those are different objects, right? And I'll talk about this in more details when I discuss linear algebra, because there are, I believe, 3 or 4 libraries in Java for linear algebra. And if you're implementing your own linear algebra library based on your desires, then maybe you don't want to write everything from the scratch. You can just interface with other libraries. Now, to show you the archive file, if you go to my math library, in the reference libraries, there is Flanagan.jar, and this is the whole library from Flanagan. And in the math, there is a class called Polynomial, and it's if we go through the structure, is very similar to what we already implemented in our polynomial. So we have a degree, which is an int, degree WZ, don't worry about this, and then coef, an array of coef, again very similar to ours. Coef WZ again, don't worry about this. And then it can create a polynomial from an int, which is an empty polynomial of degree this variable, and then coefs are all 0. So this is just empty polynomial. Has another constructor for polynomial based on an array of double values, exactly like what we did. And then of an array of float, an array of long, an array of int, an array list of objects. So you can not only you can pass a primitive array, you can also pass in array list here. And the type of object, it just determines the type of object using this method, get type code. And type code just uses the instance of method to determine what is the object. Is it byte, is it short, integer, long, float, double, big integer, big decimal. So in the array list, you cannot pass in a primitive. You have to pass a wrapper class. It is classes that represent or wrap byte, short, double, float. All right. So these are the constructors, and then polynomial, double. So it also has special cases to simplify things. I don't know why it didn't implement it as a vararg constructor. I'm going to assume that because this class was written before Java 7, because I think Java 7 was the version that introduced vararg. Java 7, I'm not sure, but yeah, that's my feeling. So it has a first zeroth order polynomial, first order polynomial, second order polynomial, third order, and a reduced poly. Now this reduced poly, we didn't implement something like this, but it's a very interesting idea, is that it goes through the coefficients and checks which coefficient is 0. So it creates a new coefficient array where it just removes the zeros from the original array. It also keeps track of the degree. So what is the degree, and which coefficients are 0, so they just throw them away. But the problem is that it uses an exact equality with a double number, and as I mentioned, this is not recommended for double numbers. So it also has a static method for reduced poly, roots tuple. So if you give it the roots of a polynomial, it creates the polynomial, and it's based on just factorizing the first order terms. Basically, if I go back here, let's say an example. So if my roots of the polynomial are 1 and -2, then I can factorize my polynomial as x minus 1 times x plus 2. It's just x minus the root. And then polynomial P11 equals x minus 1 times x plus 2. Alright, and x is the first order polynomial, and sys out P11. X squared plus x minus 2. Okay, so if you can simply write a method, you give it the roots, but the caveat here is that the roots may not all be real numbers. They could also be complex. Then it gets a bit more complicated. But in a simple case, if you assume that all the roots are real, and here it passes a double array, so it assumes that all the roots are real, then you can just simply create a polynomial. All right, create polynomial for each term and multiply it by the other terms to get the polynomial. Using operator overloading, it becomes very easy. Reset poly, it just resets the polynomial. What we said, this is not recommended because we don't want to mutate or change our polynomial. Okay, reset coefficients, copy the polynomial. So this is more like a deep copy, and then clone. It just copies it and coefficients copy just copies the coefficient, and all these are public methods. So all the methods are public because it's a green circle. Coefficients reference, get coefficient, get degree to a string, and I guess it's the to a string method here is not as advanced as our to a string degree. This is yeah, this to a string method is very simple. It's not very advanced. Two complex polynomial. So just like a polynomial with the real coefficients, we can have a polynomial with complex coefficients. Print, it just calls the to a string method on the system.out.println. Print line, print to text, it just calls the print to text method. S transform, you can Google what S transform is. S transform polynomial equals, okay, equality, you have to basically coefficient by coefficient. So the first test for equality is the degrees. If the degrees are not equal, then the two polynomials cannot be the same. Okay, so it tests for the equality of the degrees. If the degrees are the same, then you have to check equality of the coefficients term by term or coefficient by coefficient. Is equal, it's a static method that works on two polynomials. Plus, again, we also implemented the plus and double, plus int, minus, we implemented these two, times a double, times polynomial by polynomial. It adds the polynomials together exactly like what we did, creates a polynomial which is the result, as the polynomial has a degree of the addition of the two degrees. And then it wrote the convolution sum in a different way. Times a double, times nth derivative. So the derivative of a polynomial is basically another polynomial. The degree is reduced by 1. It's I'll leave it as an homework to you to try to implement the derivative and then nth derivative, evaluate, and I assume it's yes. It also implements the Horner's method. So it starts with the var3 equal times var1, which is the number, plus this coefficient. Yes, so this is Horner's method exactly as we implemented. And then nth derivative, evaluate. This evaluates the nth derivative, roots. So Laguerre polynomial, so roots. And in order to, so roots returns a complex array, an array of complex numbers. That's because roots can be in general complex numbers, and basically what it does, it creates a complex polynomial and then calls the method on the complex roots, the roots of the complex polynomial. And if we go inside the complex polynomial and actually the roots here, it calls the method roots here, and it's a little bit complicated how to implement the root finding using the Laguerre algorithm. It's called Laguerre's method or Laguerre's algorithm. That's why in the polynomial class you see this Laguerre all, Laguerre complex, Laguerre all Boolean. So you can just Google Laguerre's method to see how the roots can be found for a polynomial. And then But the point here that I'm trying to make is that you can create a public complex, and this complex should come from the Flanagan. So let's put a dependency from our build path. We put a dependency of the Mathlib project, okay, and then we're going to have Flanagan dot I'm not sure where complex is in the complex dot complex roots, okay, or we can write another method, public so the first thing I want to do, I want to write an interface method that converts our polynomial object to the Flanagan polynomial object. So Flanagan math.polynomial to Flanagan polynomial. So you cannot find let's have a look at the build path of here in the export libraries. In order to be able to have the Flanagan, I have to export it from the original project. Okay, now I think it's fine. It can find Flanagan Java archive here. So we have a polynomial P, and this is new Flanagan polynomial, and we're going to pass in our coefs, or this dot coef. So we take the coefficients of our polynomial object and return it to assign it to a polynomial from the Flanagan Java. So we're basically changing or interfacing with the polynomial class in the Flanagan library. So we can test it. So we have P11 here, which is x squared plus x plus 1. We can do a sysout on P11 to Flanagan polynomial, and because the toString method is implemented in the Flanagan polynomial, we should also see the result. And you see it's different from ours. So it's x squared, and it has this weird dot thing, so it's not the best or cleanest implementation, and it goes from the 0th order to the highest order. But now that I have this conversion, I can actually calculate the roots just by using the roots function in the, or the roots method in the Flanagan polynomial. Public Flanagan from the complex, I call the complex class, so complex here, and it's an array roots. If you write your own complex class, then you can have the conversion here too, and then return to Flanagan polynomial roots. See, it's that simple, and I can test it. So I'm going to have Flanagan complex complex class array roots equals P11 roots. It doesn't complain because it returns an array of complex type here, and then for int I equals 0, I less than roots dot length I plus plus sysout roots I, and I am going to assume that the toString method has been overridden in the complex class in Flanagan library. So we should see a nice representation of the roots. Yeah, -2 plus j0, 1 plus j0. So 2 roots, both of them are real. Let's consider P8 here. P8 and it has 4 roots because it's the fourth order. And let's also print it. So P8 is minus 2x4 plus 3x3 plus 2x minus 3, and the roots are minus 0.5 plus j 0.866 minus 0.5 minus j 8. So if you remember, I told you when you have a polynomial with all real coefficients, the complex roots should be conjugate of each other. So you see that two of these roots have the same real number, real part, but the imaginary part is conjugate of each other. And then the two other roots are real, 1 and 1.5. Okay? So this is how you can interface with other libraries and use their methods in your class. So this concludes our coverage on the polynomial topic. Thank you for listening, and I'll see you in the next video.